Yes, welcome back. We consider power series still, and now our attention turns to radius of convergence of power series. So let's hit the ground running. Okay, first of all, let's switch up the markers, and then, okay, I've missed this guy, and then let's go blue. Okay, and let's start with that. Finding, finding, okay, finding the radius, finding the radius of convergence, finding the radius of convergence is a crucial concept, the crucial concept when working with power series, okay? Radius of convergence is really important here. So the radius of convergence, radius of convergence, the radius of convergence tells us tells us the interval within which a power series converges. Okay. All right. Again, let's get introduced to power series again. You remember previously, okay, I think I want something a bit bright. So let's remind ourselves of the concept of power series. The first video already takes care of what that is in depth, but just a refresher here. So basically, we remember that a power series is an infinite series, of the form summation from n equals 0 to infinity, then coefficient a and x minus the center c raised to power n. Okay, previously I think the n wasn't put there, so let's correct that. A n into x minus c raised to power n. Sorry, yeah, raised to power n. Okay, not just x minus c. So again, where an are coefficients, and c is the center, and c is the center of the series. C is the center of the series. So now let's talk about radius of convergence. Radius of convergence. Radius of convergence. So the radius of convergence, R, is a non-negative number that describes the interval within which the power series converges, Okay. If the absolute value of x minus c, that's like the variable minus the center, if the absolute value of this is actually less than r, which is the radius of convergence, so you can say that the series converges. Okay. Then if the absolute value of x minus c is greater than r, you can say the series diverges. The series diverges, then at the absolute value of x minus c equals r, the series may converge, or diverge, and further analysis is needed, and further analysis is needed. Okay. So let's talk about methods for finding the radius of convergence. Methods for finding the radius of convergence. Of course, the methods are just the same, like the methods for testing for convergence. So methods. Okay, let me keep alternating this. Methods for finding the radius of convergence. Okay. Of course, we have the ratio test, like we've seen before. We have the ratio tests. So again, the ratio test is one of the most common methods for finding the radius of convergence. It uses the ratio of successive terms. It uses the ratio of successive terms. We did this a lot in the first video. It uses the ratio of successive terms in the series. So consider summation from n equals 0 to infinity, and you have the coefficients an, then x minus c raised by n. Don't forget, there's an n on top of x minus c, which I did not put in the first video. Please apologize for that. So to apply the ratio test, so we compute the limit. Okay, we compute. So the first thing is we have to compute the limits. The limit L is defined as limit as n approaches infinity of the absolute value of an plus 1 all over an, which we also did when we're testing for convergence. So we can now say the radius of convergence R, is given by R equals 1 over the limit. Okay, that's the radius of convergence. Okay, so if L is 0, then we can, it's clear that R is equal to infinity. R is undefined, meaning the series converges for all x. So whenever you get the limit to be 0, it means the series converges for all x. Okay. Again, if L is equal to infinity, then you see that, then you can say that R is equal to 0. The radius of convergence is equal to 0. And what this means is meaning the series converges at x equals c. That is, the series converges at the center, the center of the series, the center of the power series. So whenever the limit, you get an undefined limit, of course, in that case, and since r is 1 over the limit, so that's 1 over infinity, which is 0, then it means that the series converges at x equals c. So let's take some examples. So it's just like the first video, except that now our emphasis is on uh radius of convergence. And of course, we have this new insights that so the value of your limit is really important here. Once you get that value, divided by so it's just a 1 over that, and you get the radius of convergence. So, and you have all these conditions. So that goes. So let's have uh, one example. So example, find the radius of convergence, the radius, find the radius of convergence for the series, for the series summation from n equals 0 to infinity of x raised power n all over 2 raised power n. So what's the radius of convergence for this? So of course, using the ratio test, right? We know that this has got, so of course the limit straight is limit as n approaches infinity of the absolute value of an plus 1 all over an, okay? And that simply means that L is equal to limit as n tends to infinity for the absolute value of an plus 1. That is, anywhere you have n here, make it n plus 1. So you have xn plus 1 divided by 2n plus 1, So this is for this now. Then, of course, divided by an. So an now is the original thing you had as x raised power n all over 2 raised power n. So this is so this is an here. Okay, so we can begin to tidy all of that up so that we have L to be limit as n approaches infinity of x raised power n plus 1 all over 2 raised power n plus 1 times 2 raised power n all over x raised power n. Okay, so division turns to multiplication when we reverse the denominator and numerator. Okay, so we can tidy things up a little bit. So limit as n goes to infinity now is x raised power n times 1, times x rather, following the law of indices. So x raised power n times x raised power 1 all over 2 raised power n times 2 raised power 1. So from law of indices, we can have this times 2 raised power n all over x raised power n. So xn cancels xn, 2n cancels 2n. So we have L to be limit as n approaches infinity for x. What's happening here? Xn cancels out and we have x left. Okay, so this is x all over 2. This is x over 2. Okay, x raised power n all over 2n. An is 1 over 2 raised power n. Okay. So it's actually for the ratios. It's for the ratios. Okay. So normally we don't have to worry about the x. Sorry. So yeah, that is actually for the ratios, not for everything. We've been doing everything all along. So okay, let me just get rid of all this. We need just the an. Okay, so normally we should find the radius of convergence for the series. Okay, so here we have the an. Our an is 1 over 2 raised to power n. So it's for ratios, so that L itself is limit as n goes to infinity for an plus 1 all over an, so that we have L equals limit as n approaches infinity for, an plus 1 would now be 1 all over 2 raised power n plus 1 divided by 1 over 2 raised power n, So this is an plus 1 up, and this is an down. So we have L equals limit as n approaches infinity. So that this is now 1 over 2 raised to power n plus 1 divided by 1 over 2 raised to power n. So L is equal to limit as n approaches infinity for 1 over 2 raised to power n plus 1 times 2 raised to power n all over 1. So this is L equals limit as n approaches infinity of 2 raised to power n times 2 raised to power n times 2. So this cancels out, and we end up having L to be limit as n goes to infinity for 1 over 2. So, and that's simply 1 over 2 because n is no longer part of that expression. So we can say that L is 1 over 2. So thus, R, which is equal to 1 over L, is the same thing as 1 divided by 1 over 2, which is simply 2. So the radius of convergence is 2. So we can say, therefore, the radius of convergence, the radius of convergence is absolute value of x less than 2. So, of course, that is similar to saying minus 2 lies between x, which lies, x lies between minus 2 and 2. That's another way to say that, okay? So that's for ratio tests. Then for root test, root test. So using root test now, okay, I think this is the point where I change the markers. So for root test, the root test is another method, that involves the nth root of the absolute value of the terms. So for summation from n equals 0 to infinity, an x minus c raised to power n. So we compute the limit, which is limit as n approaches infinity for the nth root of the absolute value of an. So the radius of convergence, R is given by R equals 1 over L, as we know. So we have an example again. Find the radius Find the radius of convergence. Find the radius of convergence for the series. For the series summation n equals 0 to infinity, then x minus 1 raised to power n all over n squared. So we need to find this. Here we get the coefficient, which is an, which is equal to 1 over n squared. So applying the root test, applying the root test, L is equal to limit as n goes to infinity, and that'll be square root of n. N truth rather. Yeah, n truth of absolute value of an. So that means L is equal to limit as n tends to infinity. N truth rather of absolute value of 1 over n squared. Of course, I'm just doing this because n squared is always positive, so we don't need the absolute value actually. So that means that L is limit as n approaches infinity of the n truth of 1 over n squared. 1 over n squared. Okay, which is the same thing as so L is limit as n approaches infinity for, you know, 1 over n squared, all raised to power n, all raised to power 1 over n, all raised to power 1 over n. So L now is equal to limit as n approaches infinity. So we have 1 over n raised to power 2 over n. And as n becomes very big, right? So you can see that as n approaches infinity, that is, so 2 raised to power infinity is 0 and n raised to power 0 is 1. So we can say that the whole of this limit is actually going to 1. So we can say thus the radius of convergence, is r, which is 1 over L, and that is 1 over 1, and that is 1. So we can then say that, of course, the center in this case is x minus 1. So we can say, thus, the series converges, for absolute value of x minus 1 less than 1, because you can see the original expression has x minus 1. So that's why x minus 1 is coming up here. So absolute value of x minus 1 less than 1. If you want to simplify this, of course, this is fine on its own. But if you want to simplify this, right, that's like saying absolute value of x minus 1 less than 1 is same thing as minus 1 is less than x minus 1 is less than 1. So what can you do? You can add 1 to all sides. So if you add 1 to this side, you have 0 less than x less than 2. So it means that the series converges for values of x between 0 and 1. So what I've just done here is to say minus 1 plus 1 less than x minus 1 plus 1, because I want to remove this 1 here, less than 1 plus 1. So add 1 to all the sides. So you have x lying between 0 and 2. So like that. So in summary, the ratio test is, okay, I think this summary is really important. In summary, okay, in summary, take note that ratio test is useful. Ratio test is useful for series where terms are in the form of an x minus c raised to power n. Okay. And 2, root test is useful. Root test is useful for series, where terms, where test involves terms involve an raised to the power of n. So once you have the coefficient with something raised to power n, so root test is usually good for that. So that can help you to move fast. So both methods provide a systematic approach to finding the radius of convergence, helping determine the interval of convergence for power series. So we have come to the end of this one. Thank you so much for coming this far. If you have not subscribed to this channel, be sure to do that. Hit the notification bell so you can always get alerted when a new video is released. Also comment, like, and share. See you next time. Bye.